Hi, welcome back. We'll quickly look at the other remaining operators, basically bitwise and shift operators and the ternary operator. Yeah. So basically bitwise operator, as the name suggests, it performs the operation at the bit level. For example, if I have, let's say integer a as 8, yeah, and if I have integer b as, let's say 4, yeah, they're basically they're binary representation. If I take the binary representation of this will be 1000, yeah, and for this one it is going to be 0100. Yeah. So how do we arrive at the binary representation? It's a very simple thing. I mean, you keep dividing it by 2. For example, for the remainder is 0. This is remainder 0, and then remainder is 0. So this is how the binary number for 8 is arrived. It is 1000. Yeah. So this way we will just represent it. Yeah. Same way if I write it as 1000, and if I need to convert this into a decimal number, right? We normally put it as basically the values. For example, this value is 8. Yeah. And if this digit is 4th, this is 2, and this is 1. So if there is 1 here, that means it carries a weightage of 8. If there is 0 here, it carries weightage of 4, something like this. Yeah. So suppose if it is 1 here, then it is going to be 8 plus 4 plus 0 plus 0. Yeah, that's the decimal equivalent of it. Yeah. So coming back to this operation, so if I perform an AND operation here, what happens? AND by nature, if both are 1, it's going to be 1, otherwise it's going to be 0. So this is 0, 0 and 0 is 0, 0 and 0 is 0, and 0 and 1 is again 0, and 1 and 0 is 0. So if I perform A, bitwise B, if I perform this operation, I should get the result 0. So similarly, if instead of AND operation, if I perform, let's say, OR operation, yeah, so then what happens? Let's see. So if I perform OR operation, basically OR operation indicates essentially if any one input is 0, sorry, if any one input is 1, output will be 1. So 0 R0 is 0, 0 R0 is 0, 0 R1 is 1, and 1 R0 is 1. So output is 1100. So 1100 is 8 plus 4, that is 12. So if I perform A or B, then the result should be 12. Yeah. So that's how the OR operation is performed. So similarly, we'll quickly look at the other two operations, which is essentially bitwise complement. Complement operator is used for one operand. Yeah. So what it does is basically if I perform complement of A, that means A currently holds 1000. Yeah. If I do complement of A, then it just complements every bit. So 1 becomes 0, 1, 1, 1. So this is what 4 plus 2 plus 4 plus 2, 6 plus 1. So this is going to be 7. So that's how the complement operator works. And the XOR operator is only when, I mean, it is same as OR, but only exclusively the inputs are exclusively opposite, then it gives you 1. So for example, if it is 1000 and let's say 100, if I perform a regular OR operation, right? A regular OR operation gives me 0, 0, 1 and 1. Yeah. So if I perform XOR operation exclusively OR, so it is same as 0, 0, both are same. Both are exclusive here, so the output is 1, and both are same, so the output is going to be 0. So this is how your basically bitwise operators perform. Yeah. So you can easily write a simple program, assign A equal to 8 and B equal to 4, and simply check in your system.out.println, yeah, basically A and B output, A or B output, A complement A output, and A XOR B output. Yeah, so that should ideally match whatever we are discussing here. So that's basically a bitwise operator. So I'm not going further in detail because we hardly use these things in any of our program. But the next one, which is basically a shift operator. So essentially what they do is, suppose if I have A equal to 8, Yeah, so that is 1000. So if I represent it in 8 bits, it is 0000 and 1000. Yeah, so this is a 8-bit representation of this, right? So now if I perform A and I wanted it to be shifted basically by one time. So if I say like this, yeah, then what happens? All these bits will be shifted, uh, whatever the direction we are talking about. For example, this is a left shift here, right? By one position. So what happens is now this will be 000 and 1. This 1 has moved here, yeah, and then the remaining things will be 00. So now what happened is A was initially 8. Now what happened is this has become 16th position, right? So now this result, if I put it in B, now B is going to be 16. So what actually happened is by shifting one time towards left, I'm actually doing a multiplication of 2 because you're moving from 8th position to 16th. If you do it once again, it will be from 16 to 32, 32 to 64. Like that, it will move on. Yeah. So any left shift operation will actually perform multiplication of 2. So, and this is the fastest way to actually multiply a number by 2 because it is just manipulation of bits. And if I actually perform say b equal to a into 2, so actually system has to read the value of a and perform into operation into 2 and then write it back to b. Whereas here what happens is if I use the shift operators, the value of A is simply shifted. Okay. And that output is stored in P. So this is faster action actually. But anyway, so if whenever your requirement is actually to perform multiplication or division by 2, okay, you can actually use this. Yeah. Similarly, if I perform right shift, right? So if I use right shift operator, yeah, then what happens? You can see, for example, if A equal to 8, yeah, then it is binary representation in 8 bits is this. And if I perform simply right shift, that means I am moving the shift here. So this will become 0000 and this 0100. So whatever this extra is dropped, yeah, and whatever this vacant position is preserved with the sign. So whatever the sign is there. So in this case, what happened? A equal to, uh, let's say B equal to A right shift by one time. So if I do it this way, then actually what I'm getting is the value of B equal to 4. So that itself indicates it's division by 2 operation. So every one single shift will perform a division by 2 operation. Yeah. Sorry. Similarly, if we take this one, okay, so this is essentially called as a unsigned shift. So basically what happens is in Java, so normally if I consider it 16 bits for representing a number, last one bit um, is generally used for the sign purpose. Yeah. So if I'm starting from lower order to higher order, the last one